All right, folks, it's back in action here. In this video, we're going to continue our discussion of sum and difference formulas and looking at a few other types of problems that could be asked. This is going to really begin combining all of the things that we have studied so far. So on example 5 here, we're going to look at how we can combine our concepts and our knowledge of inverses with this sum and difference formula. Now, this example 5a can actually be done two different ways. The first thing that we could do is we could look at this problem and look at these inner pieces and first just look at, let's say, the inverse cosine of a radical 3 over 2. We know from our work with inverses that that would have to be in the first quadrant because cosine is positive, the ratio is positive, and at a radical 3 over 2, that would mean that this angle would have to be 30 degrees. Okay, our inverse sine of 1, that would be also an easy one for us to do. We would know that that would automatically then be at 90 degrees. Now, certainly we could go through the exercise of doing the cosine of the sum of these two and writing this out as the cosine of 30, remember cosine, so cosine 30, cosine 90, and then since this is a plus, we would flip it to a negative, and then we would say sine 30, and we would say sine 90. And we could continue expanding this, and we could simplify all those and get to our final answer. But on this particular problem, it's much easier for us to recognize that 90 plus 30 does give us another angle on the unit circle. So instead of going through the entire expansion and doing that work, we could just rewrite this problem as a cosine of 120 degrees. And of course, we know that the cosine of 120 degrees is going to be in the second quadrant. It's a 60-degree reference angle, so our answer, we could just jump to a -1/2. Certainly, that's going to be a lot easier for us to do instead of trying to do all the different evaluating. Now, the next problem is not going to be so easy for us to do that because when we look at both of these inverses, we have inverses that are not from our unit circle. Now, there is a possibility of combining these two types of problems. One of the angles could be something from the unit circle, and then one of the angles could be just a triangle like we're going to see here. So it's not always a one or the other. They often get combined. What we would do here when it's not from the unit circle is the same thing that we've been doing all along. We're going to draw ourselves a little triangle. Since our ratio is positive for tangent, we're going to put it here in the first quadrant. We're going to do our 5 over our 12 because our opposite over adjacent. That's, of course, an easy Pythagorean triple, gets us a 13 there. And I would label this as angle A. Then I would go ahead and I would set up my triangle for the sine. Now that ratio is going to be negative, so I'm going to draw my triangle down here in the fourth quadrant. I'm going to do my opposite of a -3, my hypotenuse of a 5. It's again an easy Pythagorean triple, so I can fill that in as a 4, and I would label this as angle B. Now I like to go ahead and write out my little formula because it helps me visualize better what I'm going to substitute. So it's a sine formula, so it's going to be sine, cosine, cosine, sine. And of course, since this is a minus, it's going to stay the same as a minus. And then I'll have my A, B, A, B. And now I can just read from the triangles that I've created. So for the sine of A, I'm going to go to triangle A. So I'm going to say opposite over hypotenuse and grab that very quick 5 over 13. Then cosine of B, I go to my other picture, adjacent over hypotenuse, and I can grab that 4/5. Continuing on, now I'm going to go get the cosine of A. So I'm going to come back to A, and adjacent over hypotenuse gives me a nice 12 over 13. And the sine of B, I'm back to this, and I'm going to do opposite over hypotenuse, and I want to make sure to grab that negative. Don't lose that negative. That's where if you don't draw your triangles properly, it's easy to get them confused. Now, just like we've seen before, all the denominators are going to be the same, so I'm going to have a nice 20 I'll have a minus this negative, so I can write that as a plus 36 all over 13 times 5 is 65. So my final answer is going to be 56 over 65. Okay. Now, the next thing that we're going to look at are identities. And I know sometimes students don't really like identities, but truthfully, these identities turn out to be the easiest of all the identities that we're going to do. Just like before, you could technically start on either side. It's certainly going to be easier for us to start on the left. That's just typically the way I set them up for you to do. So what we're going to do is we're just going to expand this with our sum and difference formula. So I'm going to say tangent of 2 pi minus tangent of theta is going to be all over 1 plus, remember I flipped the sign in the denominator, tangent 2 pi, tangent theta. Now, of course, tangent of 2 pi is the same as tangent of 0, and tangent of 0 is 0. So I'm going to have 0 minus tangent theta all over 1 plus 0 times tangent theta, which means this is going to cancel out. That 0, of course, is gone. So I have a negative tangent theta over 1, or the negative tangent theta that I wanted to get. So like I said, these are often much, much easier for us. Let's go ahead and take a look at another one. We're going to start here on the left. And the first thing that my eyes are drawn to is the fact that I have this sum and difference in the numerator. So I want to get that expanded right away because I can't do much with that like that. So now I'm going to have my cosine. Oh, I did that again. So I'm going to have my cosine, cosine, sine, sine, A, B, A, B, and since this is a minus, I'm going to flip that to a plus. This is all going to be over sine A, cosine B. Now, this one sometimes is a little confusing for students of what to do. So what we're going to do is we're going to recognize that I can take this portion of the numerator and divide it by that, and this portion of the numerator and divide it by that. So I'm going to split it back out into its own separate fractions. So cosine A, cosine B, all over sine A over cosine B, plus sine A, sine B, all over sine A and cosine B. Now what I can see is that my cosine B's are going to cancel, and of course cosine over sine is cotangent A. On the next one, I can see my sine A's are going to cancel, and sine over cosine is tangent, so that's going to give me a plus tangent B. And sure enough, that's exactly what we wanted to see. Now, this last problem has a lot of algebra going on in it. And what we want to notice is that we can't do our normal Pythagorean substitutions like we would like to be able to do, because we just have sine and cosine. So what we're going to do is we're going to isolate the sine and the cosine. We're going to split them apart, get one on each side. So I'm going to go with square root of 3 sine theta, and I'm going to move that cosine theta to the other side. I could have moved either one. It didn't actually make a difference. Now what I want to do is I want to get these so that they're squared so that I can start to do a substitution. So I'm going to square both sides. Squaring both sides of the problem is going to introduce some extraneous solutions for us, so we need to be careful. On the left side, we're going to end up getting a 3 sine squared theta. On the right, I need to FOIL that, so I'm going to get a 1 minus 2 cosine theta plus my cosine squared theta. Now I can introduce a Pythagorean substitution, and my eyes are going to be drawn to the sine. Since I have 2 terms with cosine, sine is going to be the easier substitution here. So I'm going to do 3. I just like to do that one, don't I? Then I'm going to do 3 And sine squared, of course, replaces with 1 minus cosine squared theta. Don't lose these parentheses, it'll mess you up. 2 cosine theta plus cosine squared theta. Now I'm going to distribute 3 minus 3 cosine squared theta. Everything on the right stays the same. Nothing's going to change there. Now, I'm going to need to factor, so I'm going to shove everything to the right-hand side so I can keep my squared term positive. So I'm going to have a 0. That's now going to give me a 4 cosine squared theta. Moving then I'm going to have my minus 2 cosine theta. Moving the 3 over, that's going to give me a minus 2. Now, what I notice is that everything here could reduce by 2. So when I go to rewrite up here, I'm going to reduce everything by 2 immediately, just to make this process a little easier for us to factor. 2 cosine squared theta minus a cosine theta minus a 1. Now let's factor. 2 cosine theta, cosine theta, and then I'm going to have a plus 1 here and a minus 1 here, and that'll get us to the factoring that I want. That means that cosine theta equals a negative 1/2. So theta could be 2 pi over 3 and 4 pi over 3. Or my cosine theta could equal, theta could equal 1. So my other answer, potential answer, could be 0. Now, I mentioned at the beginning that when we square both sides, we're introducing the possibility of extraneous solutions. So you've got 2 options for how you can check for the extraneous solutions. Option number 1 is to, when the video is done, go to Desmos, and you're going to type in this left-hand side is one graph, the right-hand side is one graph, and when you look at where they intersect, you'll find that they actually only intersect in 2 places. And that means we are actually going to throw out this one. When you go to the graph, you'll see that that one can get thrown out. Your other option would be to algebraically check each of the solutions on the original equation, and you'll find that one of them that this 4 pi over 3 will actually still give you an untrue statement. So I'm not super worried about going through that here in the video. I'm going to leave that for you. The Desmos is the very quick way to understand and see that, sure enough, that 4 pi over 3 is an extraneous solution.